Okay, so okay, the last part is on the quotient, I think. Quotient. Okay, normal subgroup. Then quotient group. Okay, so H is normal in G. H is normal in G if and only if the left coset is equal to the right coset for all element A in G. And this is the normal subgroup. Yeah? H is normal in G. The quotient group, of H in G, some books call it a factor group. Factor group. And we use G mod H. That is how you say it. G mod H. Yeah. This is all the left or right coset. In my class, normally I will use the left coset, but it's true also for the right coset. It's just the list of all the cosets. Okay. So this is called the quotient group. And this can be only defined for the cases in which H is normal in G. Okay, you don't consider this if H is not normal. And there is this very important theorem. If G is a billion, then H is always normal in G for all subgroup. If G is an abelian group, or if G is a billion, then H is normal in G for all subgroups. For all H subgroup of G. Why? Why? Because this means okay, because this actually means A times little h, right? And if G is a billion and H is a subgroup of G, then H is also a billion. Because this is a subset, right? If G is a group, H is a subgroup of G, by definition is a subset. If G is a billion, every element commute. Every element in G commute, every element in H is also element of G. So in a way, every element in H commute. So H is also a billion. Okay, then this A is in G, this A is in G, this H is in H. So A times H is also in G. This is HA, right? Which is also equal to HA. This is actually the proof of this, right? This is the theorem who knows, I might ask you a question, right? Prove that if G is a billion, then, or I can say it in words, every subgroup of an abelian group is normal. Okay, that can be said in words. Every subgroup of an abelian group is normal. You have to write like this, and using the definition, this is the proof. Okay, now I give you one example, yeah? I give you this before, but I give you again. So Z is ... 3 dot . Okay, and then a subgroup. I need a subgroup of Z. Can somebody give me a subgroup of Z? What is a subgroup? Nizam? Jangan lama tak panggil nama Nizam. Are you here? Muhammad Nizam. Ya.
Yes, Prof.
Mana mukanya? Tunjuklah sikit.
Huh?
Give me a subgroup of Z.
Whole number.
Whole number. Whole number meaning start from apa? 0 or 1?
From 0.
From 0. But it is not a subgroup. It's a subset. I want a subgroup. There is no negative, so it cannot be a subgroup.
Rational number is a subgroup, Prof.
It's not a subgroup. It's not a group. Is it a group? If you do like this, it's a subset, but it's not a group. Right? Even if you put a 0, it's not a group because there is no inverse under addition. Anyone else want to help Nizam? Anyone? Nak type pun boleh.
Z.
2Z. Okay, 2Z. 2Z. It's okay, but then you don't have that many. Let's try 3Z, yeah? Okay, 3Z, yeah? Okay, 3Z. Why I don't want 2Z? Because then you only have 2. Ini saya dah bagi hari tu ni. 3Z, like this, right? Z is here, multiplied by 3. Right? Multiplied by 3. So the first one, we call this H, yeah? H is this. Oh, tak boleh balik lah. Boleh H je lah sini, ya? I just put this H. Okay, so you will cancel all this number here, right? Tak banyak pun. Okay. The second one is 1 plus, yeah? Plus H. The second one is take the second number here from G. Take the next one. Add to this. Add 1. Right? Okay, then you cancel. 1, another 1, and this one. -3, okay already. Okay, left, one left is 2, right? 2. 2 plus H. 2 plus H at 2. 7, -4. Add 2 to here. -1, 2, 5, 8, 11. Okay. Then if you write this longer, you will actually cancel all the rest, right? 2 and then -4. So it's all cancelled. Maybe meaning it's all used already for partition. Actually, we are partitioning the whole original set into groups, into subsets. Groups kumpulan, not groups. Sabutlah bahasa Inggeris ni. Like you have one class of 33 students, you want to partition into 3 groups or subgroups or subsets. So there is 11 person in one group, right? 11 times 3. This is what actually cosets are. They're all the same size, okay? And you don't have any intersection. And then it becomes your coset, because this is an abelian group, because for integers, a plus b is b plus a. So it's abelian, okay? So the left or right coset, they are the same, because addition you add here or you add that way is the same, right? So H is normal in G, because G is abelian, right? And the coset, you put the coset like this. You have only 3 coset. Okay, you have only 3 coset. And this become a group. A group consisting of cosets which are actually infinite. Okay, the original group is infinite. The coset, the size is infinite, but the quotient group is finite. It has order 3. Order means the number of elements. 3. Then you can make this a finite group. Originally from infinite group becomes a finite group. And you can make a Kelly table, because this is a finite group. Then the Kelly table will be, let me not delete and write here. Yeah? Hopefully it's not too small. Kelly table, this is 1 element, 1 element, 1 element. So how do we add coset? Okay, how do we add coset? The formula is A plus H plus B plus H, 2 coset. How do you do operation on coset? Is by adding the representative of the coset. How do you add 2 cosets? Is by adding the representative of the coset. Okay, and keep in mind, remember that this coset is equal to H is equal to 3 plus H is equal to 6 plus H is equal to 9 plus H. They're all the same coset because they have the same number of elements. That's why once we cancel, they're all elements inside here already. You don't need to do it again. Okay, so how do you add? If you don't see it, that means actually 0, right? You see just H, what do you want to add? That is a 0. So there is a 0 here actually that I don't write, because it's the same as 0 plus H. Okay, so this plus this is just, right? That is a 0. This, the same here, and the same here. Fill in the blank, 4 more. Let me see my pin. Oh, it's clear. Okay, that's good. All right. Okay, what's the answer here? 2 plus H. Abid?
Yes, yeah.
What's the answer here?
3 plus H.
3 plus H is not a part of any here, right? If you add 3 plus H is not here. To be a group, it has to be closed. But 3 plus H is H, right?
Mm-hmm.
I didn't write, but this is actually equal to whatever element inside plus H. Like this. This one is 1 plus H is also equal to 4 plus H, 7 plus H, negative this plus H, right? So you will write here H. Abid, okay?
Okay. Got it.
Okay, nangis?
Sila. Saya tekan.
That is actually laughing until you cry. Okay. Nabiha. Siti Nur Nabiha.
Yeah, Prof.
What do I put here?
H.
Yeah. Okay. Shazwani, Nur Shazwani. Ada tak?
Yes, ada.
What do I put here? 2 plus 2 is
4 plus H.
4. Then you find here.
1 plus H.
We know that this is a group, so the only element left, which is not yet here, is 1 plus H, right? But actually we add 2 plus 2, 4. There is no 4 here, but there is 4 inside. So it's equal to. So you see, they're all elements from top, right? Okay. And if I ask you what is the identity? The identity is H. Because you add, this is similar to the top of this, right? And what is the inverse? The inverse of H is H. The inverse of 1 plus H is 2 plus H, because when you add these two, you get the identity. So this is like a group, right? So I can say actually this, sometimes the question is like this, show you remember this time I give you the group of addition modulo 3, right? It has 3 elements. This one is this. So actually you can show there is a mapping from this to this, in which you will map this to 0, you can map this to 1, and you can map this to 2. It's 1 to 1 on 2, and you can show it is a homomorphism. Okay, so this is a group. So you can visualize this coset, although the cosets are infinite, but it's considered the identity just like one element, which is actually inside is infinite. Okay, so that's it for that chapter. Yeah. Okay, any question? Let's go to, if Hannah or Shiham, you can help me share the exercise of this chapter. We just look at the exercise. I give you some hints. Okay. Okay, so exercise 1 to 4, determine whether the description is a valid definition of a binary operation. Meaning, if you perform that operation, does it fall into that set? Is the set closed under the operation? Ya, saya tak sempat nak panggil nama seorang-seorang. Kalau dalam kelas senang, okay, kan? Tapi kita tak sempat. Selamat. Okay, I'll just go through. I give you the hints. Okay, naik atas sikit. Tu turun bawah, naik atas sikit. Okay, on R, real number, where A, B is ordinary multiplication. So just check on some general thing like a real number times a real number. Or maybe you can put yes or no lah for number 1, without me asking your name. Is it binary? When you multiply two real number, is it a real number? Cepat type, yes, no, yes, no, yes, no. Menong pula. Malas sangat nak type, bagi jempol ke bawah. When you multiply, okay. Multiply two real number, do you get a real number? Yeah, okay. Number 2. Integer, yeah? 1, 2, 3. Okay. You multiply, not multiply, A to the B. A to the B is A times A times A times A. Okay. Yes or no? Cepatlah, takkan seorang je yang jawab. Okay. Hannah and Shiham, you have to answer too. Okay, G is Z. Okay, A star B. A star B is A, so the B. So you have to think when it's Z, there's a negative, there's a positive, right? And A, you can give some examples. If, if B is Z plus, A to the B is A times A, right? Times A, B times. Like if B is in Z plus, A is also in Z plus, right? So just give some numbers to A and B. Give me some numbers. A, maybe 2, B, maybe 3. So you have 2 to the 3 is 8. And you have to check whether 8 is in Z or not. So 8 is in Z, yes. But you have to try also the negative. If A is in Z negative, B is in Z positive, so you get something like negative 2 to the 3, which is negative 8, still in Z. What about B is negative? So if A is in Z, B in Z negative. Okay, this is Z, right? A say is 2, B is negative 2. What is A to the B? What's the answer? 1 over 2 squared, which is 1 over 4. 1 over 4, is it an integer? Dah giling tu. Siapa yang giling tu? Fatana. Baru nak giling. So, for number 2, the answer is no. Tengok siapa yang jawab no. Semua jawab yes. Tak fikir dulu ni. Okay, so that's why baru betul nak nangis. You have to think about the positive and negative. How do you write the answer? You will say that this is not a valid definition of a binary operation since, for example, take A to be Z, B is, take A is 2, B is negative 2, then A to the B is 1 over 4, non in Z. So it is not close. Okay, this is the only reasoning that you will put. If it's yes, then you put, this is not the answer. You have to write like this. You will put in Z. Okay, in general. All right. Okay, so next is, you can do 3 and 4. Okay, you can do 3 and 4. All right. 3 and 4, check. Okay, number 5, commutative or associative. Easy, right? If it's a plus, and if it's just a regular number, you can check A plus B plus C. Is it A plus B plus C? And division, we have done this. Real numbers, if you include 0 under division, then that is not close because you cannot divide by 0. Okay, next, number 8, commutative. Fill in the blank. So the binary operation is commutative, means it has to be symmetry. Okay, next, number 9. Binary operation defined. Next, compute, multiply. C times D, is it equal to D times C? So if it is not equal, then it is not abelian. And do the rest. Okay, number 10, you want to define a semigroup. You have to check the associativity and then see if there is identity, then it is a monoid. Okay. Next, Z plus. I've gone through number 12, 13. Okay. Okay, next, 15 is associativity. Okay, number 17. I've done this. Ln. Okay, rational number. Number 22. The set of odd integers under multiplication. How do you show or decide, yeah? Is it decide? Yeah, determine, right? Is a group or not? Okay, call it S. This is number 22. S is the set of odd integers under multiplication. Anybody wants to give your answer in the chat, or better unmute and share why it is, why it is not. So you have to check S actually non-empty, right? Odd integer under multiplication. So you want to do like this. What is the identity? One, right? And one is odd. Okay, associativity, yes, under multiplication. Odd integer. Odd integer, yeah. What about odd times odd? Odd times odd is odd. How do you show? So you can do 2x plus y times 2y plus 1. 2x plus 1 times 2y plus 1 equals 2 times something plus 1. Yeah, that's in general. Okay, but there is no, this is the identity, right? There is no inverse. Actually, the answer would be it is not a group because not all element has an inverse. This has inverse because 1 is the inverse of 1. How do you show it? Because 1 times 1 is 1 and 1 is odd. So 1 has an inverse, but all the other has no inverse. Oh, negative 1, right? Negative 1 also. Negative 1 times negative 1 is 1. So negative 1 is the inverse of negative 1. But what is the inverse of 3? 3 times what is 1? 1 over 3. 1 over 3 is not odd. Okay? 1 over 3 is not in S. Okay, so you think first, you write first, scrap paper, but your answer would be S is not a group since there is no inverse for all elements of S. Okay, except for 1. All right, okay. Do we have anything else in there? Okay, none.